Good afternoon. Let's get started. Our speaker next week will be Kate Galbraith of the Texas Tribune. She will talk to us on energy in media, a journalist's perspective on covering energy. Today's talk was originally designed as a panel discussion, and we had a second panelist, Lee Lane, who could not join us because his travel plans were disrupted by Hurricane Sandy. So we apologize for that change in the design of this talk. So our sole speaker today will be Dr. Eric Bickel. Eric is an assistant professor in the mechanical engineering department here and also in the petroleum and geosystems engineering. Eric's research interests are in the theory and practice of decision analysis and its applications in energy and climate change arenas. He has done a range of work, and you will see how interesting all of that is and how relevant in terms of understanding what types of technologies we should be thinking about in the context of climate change once you try to understand really the range of impacts and the risk distributions associated in the context of climate change. Eric holds a master's and PhD degree in engineering economic systems from Stanford University. Please join me in welcoming Eric.
Okay, good afternoon, and thank you very much for inviting me to speak. And again, I'm sorry Lee couldn't make it. Lee and I have worked together over the last couple of years, and he would have been a very nice complement to tonight's talk. So I'm sorry he can't make it. I'll debate myself maybe and then change my mind here at the end. Okay, so what I was asked to speak about is climate change and climate engineering, and this might be somewhat of a controversial topic, but presumably in academia that's okay, right? We can talk about that, and we can talk about what this is and some of the maybe benefits and some of the risks. So let's I'll just give you a brief background and some pointers to some things if you want to learn more about this. I worked, I'm going to go into the details, but in 2009 I was involved in a project with what's called the Copenhagen Consensus Center. I'll explain how that process works, but essentially people write papers on different topics. They present to an expert panel. Expert panel ranks, these are solutions to climate change in this case. And then all the papers are in a book. Okay, and so part of what I'm going to talk about, the papers are in this book that I have up. There was, Butler can correct me, but I think I'm the only decision analyst in the Internet Movie Database. I'm claiming that, so you check that. So while I was doing this work, there was a movie being filmed. It's called Cool It. You can get it on Netflix if you're interested. And so I make a very brief appearance in that. It's not just cameo like I happen to walk by the camera or anything. But Lee is featured a little bit more prominently in this. And he's up there with the headshot and his name and affiliation and so forth. So you might be interested in that. And then in 2000, and I'm getting old and confused, but 2012, I guess, maybe it was 11, but we did another project with the Copenhagen Consensus Center. It was, this time, wasn't just looking at climate change, it was looking at all the world's problems, and I'll describe it, but there's a report. You can go to their website. This report's up there where I talk about some of this, but there's other things up there about climate change and other challenges. And then finally I have a new paper out in Climactic Change that looks at some of the economics of this climate engineering or geoengineering. And you should be able to pull that down if you'd like. It's only online now. It hasn't been in print yet. Okay, so these two studies here, Copenhagen Consensus projects, the way they work is in 2009 they posed this thought experiment. Let's say the global community had $250 billion per year to spend over the next 10 years, so $2.5 trillion, to diminish adverse effects of climate change and to do the most good, basically what should we do? Okay, so they recruit people to, as I mentioned, write papers on different topics, different responses to climate change. And then they get at least 2 people to then write papers critiquing the paper that you wrote. Okay. And then you present your analysis and your solution to an expert panel. And as you can see, very illustrative expert panel in this case. There were 3 Nobel laureates on this panel, and then Nancy Stokey, who's a professor at the University of Chicago, and then a professor here from Columbia University. And I have a picture of that in just a moment. And then in 2012, so 2009 was just climate change. If you were going to just double-click on climate change and go in and rank all the solutions, what's the ranking? In 2012, they redid a more standard study that the Copenhagen Consensus does, and that's where they rank all the world's problems. So here, the idea was we've got $75 billion over the next 4 years to address problems that the world faces, like malnutrition, hunger, warfare, corruption, climate change, and so on. And they recruited people to write papers on that diverse set of topics. You present to this expert panel. It was the same except for Bob Mundell from Columbia replaced Jagdish Bhagawati. And again, so we presented to the panel. People write critiques of your paper, and then this expert panel does the final ranking. Okay. This is a picture of when I did this in 2009, and just seated around the table. This is the intimate setting. It was like, I'm a big baseball fan. It was like, presenting to Thomas Schelling. It's like if Babe Ruth called you up and asked if you wanted to play catch, right? It was I love baseball, so it was a really exciting experience. Me right here with the Nobels, and then Lomborg is in the blue shirt there. And this is at Georgetown University. It was in an old library there. It was just a neat experience. Your version of Moneyball. Yeah, my version of Moneyball. Yeah. Okay, and just another shot, and then the other people I wanted to show you. Gray hair on the right, that's Lee. That's not a very good shot of him, but there's Lee's picture there. Okay, that's Lee. And then on the left is Roger Pilkey Jr., who some of you are probably familiar with. He was one of the people that wrote a paper about our paper. And then Ann Smith in the middle, she is with Charles River Associates. Okay. All right, so here's the results from 2009, and then I'll go into analysis behind these. This is the ranking of the expert panel in terms of the solutions. And we worked on what they have here ranked first, climate engineering. This is research. So what we did, we recommended research into this topic called climate engineering, which I'm going to cover. And there's different flavors of climate engineering. Okay, so one of them is this thing called marine cloud whitening. They ranked first. Second, they said technology-led policy response. It's primarily energy, R&D. Second thing was climate engineering with the stratospheric aerosol insertion, which I'll talk about. And then we also worked on number 6 there, which is, let me show up. Number 6 is air capture, which is another type of climate engineering, but fundamentally different from the first 2. I'll explain. Okay, and then in 2012, did this again, but again, this is all the world's problems, not just climate. And so then they rank those, and you can see that the things at the top tend to be problems that are afflicting many people now. And so the first was investing in hunger and education. You can go on the website. I don't remember all the solutions underneath these. But an example might be funding for research into an AIDS vaccine. That might be something that would come under like infectious disease. Okay, and then you could look down the list, and then the first climate solution is 12th, and that was geoengineering R&D. So again, in terms of climate solutions, the expert panel ranked research into this area first, and there's other climate responses further down the list, but again, the things at the top are really problems that are affecting people now that you could potentially address now. Okay. All right, so the argument for this talk is, well, I'll step through it and then I'll build on this as I go throughout. So first thing, all else being equal, anthropogenic emissions of CO2 are going to warm the Earth. Okay, how much they're going to warm the Earth is uncertain. Right? This warming will, on balance, result in economic damages, okay? Because we've designed our current system for the current configuration, and if it changes, then that's going to be costly to us in some way. There may be some benefits and some costs, but on balance, there'll be a cost. It's unlikely that negotiations will have an impact, significant impact on temperatures for many decades, and that's just, first you'd have to have an agreement, and then second you'd have to have reductions, and then third, CO2 would have to start coming out of the atmosphere, and then fourth, the Earth would have to start cooling in the oceans, and that will take some time. Emissions reductions, even steep ones, can't eliminate the possibility of significant warming. And I'll have a few slides on this, but it's possible that with the CO2 we've already put into the atmosphere, we're already committed to some significant amount of warming that we may not, we're uncertain about the range, and it's possible that it could be significant. And also that emissions reductions don't really give us any ability to respond in an emergency. Okay, if there was some climate emergency, President comes on television, the West Antarctic ice sheet has disintegrated or is going to disintegrate, in the next year or something. Emissions reductions are going to work more slowly. So, fourth, the argument then is we should consider additional approaches. That includes climate engineering. There's one particular technology known as solar radiation management, and it might be able to effectively lower the risk of passing tipping points in the climate system. But the technology doesn't exist. Its risks aren't really completely understood. So therefore, we should invest in research and underline research into this area. And then if successful, we should develop it and be prepared to deploy it. But the decision on the table is not should we start doing this tomorrow. The decision is should we start building capability. So if we think we need this, that we could do this. Okay, so just quick background. This is, I think, probably familiar to most of you here. Of course, there's two types of radiation that we're worried about in terms of global warming. There's shortwave sunlight, long-wave heat, and this is a diagram which shows how much energy we're receiving from the sun in terms of watts per square meter. So coming in, we've got 341 watts per square meter, and this is averaged 24 hours and around the Earth and around a year. So it varies, but that's the average number. 79 watts per square meter are reflected back into space by clouds. 23% there on the left is reflected by the surface. So we've got about 341 coming in and about 102 going out. So that gives this planetary albedo, how bright the planet looks, of about 0.3 that I have there on the right. Okay, and of course some of this energy is then absorbed by the atmosphere and by greenhouse gases. It's then re-emitted in terms of long-wave radiation in all directions, and then of course some fraction of that comes back to the surface, right, creating an energy imbalance. Okay. But just the magnitude of these numbers, I think, are important to understand for what we're going to be talking about. About 341 coming in, 102 going out. Okay, so human activity contributes to climate change and global warming. Of course, greenhouse gases in the Earth's atmosphere cause the planet's surface to be about 59 Fahrenheit warmer than it would otherwise be the case. So if you're a mechanical engineer, you can do black body radiation calculation of what the temperature of the Earth would be if it had no atmosphere. And it would be much, much colder, right? There were no greenhouse gases. And I've covered most of this. The greenhouse gases allow the passage of shortwave radiation, but they absorb the long wave and re-reflect it, or re-radiate it. Burning of fossil fuels is going to alters the Earth's carbon cycle, leading to a buildup of accumulation of CO2. And thus far, we've warmed about 1.3 Fahrenheit, while CO2 has gone up about 100 parts per million. Okay, so from 0.028% to 0.038%.
Since industrialization?
Yes. Yeah. All right. Thanks, Bruce. Okay, so the way a lot of these models work, and what I do here, there's a critical uncertainty, as you can appreciate, which is the climate sensitivity. That's how much warming would you get for a doubling of CO2 concentrations. Now, the way they actually do it, it's what energy imbalance do you get for a doubling of CO2, and then how does that energy imbalance translate to temperature? So, but if you put those two things together, you've got a doubling of CO2. What does that mean in terms of temperature? That's how people generally describe it. The IPCC has this statement that the sensitivity is likely to be between 2 and 4.5 Celsius, with a best estimate of 3. It's very unlikely to be less than about 1.5 C, but values above 4.5 C can't be excluded, but there's more uncertainty about those. They have another document where they define what these verbal statements mean. What do we mean by likely? What do we mean by very likely? Likely, they mean there's greater than a 66% chance. Very unlikely is less than a 10% chance. So what you can do is you could take that top statement, and what I've done here is I fit a log normal distribution to that. Okay, so with the idea that adding CO2 is not going to cool the Earth, okay, so it can't be less than 0. And then what I've done is I've fit this log normal distribution so that the mean is 3. And then you can see, if you do that, there's about an 80% chance of that a doubling of CO2 would result between 1.5 C and 5 C of warming. But there's a lot of, there's an order of magnitude uncertainty there, right, in terms of from 1 C up to 10 C, in terms of what doubling of CO2 actually means. Okay? And of course, there's also uncertainty what the impacts would be. This is a IPCC chart, has the temperature change on the bottom, global mean annual temperature change, okay, relative to 1980, 99 over this time. But what they're doing here is they're just projecting what would the impacts be of different levels of warming, right? And you can imagine the probability distribution on warming across that. So we're uncertain about temperature, and we're uncertain about what that means to us in terms of damages. And I won't go through all the different ecosystems here, but clearly there's some significant impacts, and more significant as temperature increases. Okay. So in addition to this, the scientists are also worried that the climate system might contain tipping points, that if you go beyond, that the system would transition into some other state, right? And you can't just back up, right? So that might be loss of Arctic sea ice, melting of Greenland, Antarctic ice sheets. There's a study I have here, Lenton et al. They looked at all these different possible tipping points or thresholds, and they tried to prioritize them in terms of their proximity and their impact. And they're most worried about loss of Arctic sea ice and melting of the Greenland ice sheet. And of course, if Arctic sea ice melted, then the darker ocean below would be exposed, and then instead of some of that I showed getting reflected back into space, more energy would be absorbed. They conclude that a summer ice loss threshold, if it's not already been passed, it's very close, and the transition could occur well within this century, okay, in the Arctic. All right, so against this backdrop, I think one thing is clear, and that's that 20 years of negotiations have failed to reduce emissions, and emissions have increased over this time, and this is an area I think Lee could have addressed in a lot of detail, and citing Lee here. Many reasons for this, including the fact that some large countries have large populations in poverty. Okay. All right, so that's background. Now that I've depressed you, right? Now hopefully I won't scare you. Yeah, too bad. So what is climate engineering? The Royal Society defines climate engineering or geoengineering. I'm using those two terms interchangeably, but I prefer climate engineering because we're really talking about the climate, and sometimes geo has other changes to the Earth's surface. It's the deliberate large-scale intervention in the Earth's climate in order to moderate global warming. And the Royal Society put out this report in 2009 recommending research into this area. National academies had a workshop on climate engineering. It's been a few years ago. And then the House had, this was maybe 2 to 3 years ago, had hearings on climate engineering. Lee testified as part of that. And then the House of Commons in the UK has also had hearings on this. So here's a schematic that I like from Linton and Vaughn's paper. There's two different families. There's air capture and solar radiation management. Air capture seeks to remove CO2 directly from ambient air, okay, and then sequester it like you might do with carbon capture and storage. But instead of capturing CO2 from flue gas, you're pulling it directly out of ambient air. There are different ways to do that. One would be on the right, there's sort of this air capture and go into geologic storage. Those are like artificial trees. There's a professor, Klaus Lochner at Columbia, who's working on these giant artificial trees that would pull CO2 out, and then you can separate it and store it. Another idea is adding nutrients, iron or something, to the oceans and causing algae blooms, and which would uptake CO2, and then they would die and they'd go to the bottom of the ocean and sequester it. I'm not going to focus on air capture primarily, I guess, for two reasons. One, it also is going to act relatively slowly, just depending on how quickly you can pull out CO2, and it's also very expensive, as you can probably imagine, and if you're familiar with carbon capture and storage. But the concentrations are so low in ambient air that it's very expensive to try to pull CO2 out of ambient air. When we wrote these papers, it was about $1 trillion per ppm. So every ppm that you wanted to remove from the atmosphere would cost about $1 trillion, and we're up 100 ppm. So it's a fair amount. I want to talk about the other category, and that's solar radiation management. And there, the idea is to change the albedo of the Earth in some way. Different ideas for doing that. At the highest level, these sunshades and mirrors in space, which you may have heard about. Roger Angel at Arizona has this idea for launching tiny mirrors, and they would sit at the Lagrangian one point between the Earth and the Sun, which is sort of a balance point. Doesn't take a lot of energy to stay there, and you would reflect some fraction of sunlight away. That is very expensive. There's large fixed costs to that, so I'm not really going to address that. Stratospheric aerosols, the idea is that, as I'll show you a slide, but currently aerosols are offsetting some amount of global warming. Okay, sulfur dioxide in the atmosphere reflects sunlight back into space and is already providing some cooling. And another thing that's sometimes mentioned is volcanoes inject sulfur into the atmosphere, like Pinatubo, and then there was cooling after that. Okay? Although what you do here would be on a much smaller scale. There's increased cloud albedo, and the idea here is that clouds need something to condensate on, and if you look at ships from space, you'll see clouds forming behind ships, and that's from the sulfur and the diesel fuel. And so this is occurring, and the idea would be, well, maybe we could inject salt. We could shoot up seawater, and then that would cause clouds to form above the ocean. So different scientists working on different ideas here. Okay. So what attracts me is, this is an interesting decision, right? A lot on the table, a lot of uncertainty. So the reason I got interested in this to start. I'm primarily focused on the two that I've colored in red there. Now here's an IPCC chart which shows the radiative forcing from different human activities. If you look at the very top, you've got, well, what's the energy imbalance caused by CO2? And it's 1.66 watts per square meter that they have there to the right. That's the mean, and then there's some uncertainty around that. And then you've got methane and so forth. So there's things we're doing that warm the Earth. And then the blue, you see the effect of aerosols that the IPCC estimates. The direct effect is this aerosols directly reflecting sunlight back into space, kind of like the stratospheric aerosol. And then cloud albedo is the second thing that I talked about, with clouds forming because of the aerosols. Together, those are offsetting about 1.2 watts per square meter currently, right now. And there's more uncertainty about that, you can see from the bars, and this would be updated in the new IPCC study. So, so one thing is just that this is happening. It's not proactively right now, right? But this effect is going on. We're doing things to warm the Earth, and we're doing inadvertently things that cool the Earth. All right, so let me talk about, I have 10 minutes, right? That's incredible. Like a time warp, yeah. Okay. So let me tell you about a model that I use to look at this. It's called DICE. And this was built by Professor Nordhaus at Yale University. And it's an integrated assessment model. What it does is it links economic activity to CO2 emissions, and then CO2 emissions to a buildup of CO2 concentrations, and then concentrations to temperature increases, and then temperature to damage. So the idea is this model would allow you to say, well, if we reduced emissions by a certain amount, we might lower economic output, but we'd also lower damage from climate change, and there's some optimal way to do it. The idea is to solve for what's the optimal way to reduce CO2 emissions over time, okay, is what this model solves for. There's some math. I won't go through it, but the output looks something like this. The green line is what Nordhaus calls optimal controls, and this is the least cost way, the least cost path to phase out CO2, and you can see it starts with about a 18% reduction in 2015. It runs on a decadal scale, so 2015, and phases out CO2 over about 185 years. The maximum temperature increase over that time is 3.5 C. Okay. DICE is all deterministic. It's a deterministic model. You set all the parameters, and then it says, here's the path. Now you can tell DICE, you might say, I don't like that. I want to limit temperature change to 2C, and that's what I have there in the kind of red, L2C. You can put a constraint, okay? DICE, you figure out the cheapest way to hold the temperature to 2C, and it would give you that plot there, and you'd need about a 20% reduction in 2015, and then phase out CO2 over about 80 years. And then limiting to 1C, you would have to have about a 35% reduction 2015, and then phase out CO2 over about 50 years. The bouncing around there is just the optimization. Once it phases out CO2, it's a little bit unstable. Okay. It then produces the economic cost of these different scenarios. If you don't do anything in DICE, DICE estimates that climate damages, the present value of climate damages are about 22.5 trillion. Maximum temperature increase of 5.2, and that's in today's dollar. That's in 2005 dollars. Okay. Optimal controls it does some emissions reductions. That's abatements. It does 2.2 million present value of emissions reductions, and it lowers climate damages to 17.4, and the total is 19.5. So it's better, which by definition it's optimal. So that would be better, but you can see that still the optimal policy is structured to accept a large degree of climate damage still. Okay, that's 17.4 versus 22.5. Limiting to 2C does 11.8 million in abatement, lowers climate damages to 13.4, but the total is 25.2, which is worse than doing nothing. So in this model, limiting to 2C is worse than doing nothing, right? And the same with 1.5C is, of course, worse. Okay, so the question is, what are the biggest uncertainty drivers in these estimates? DICE is, again, deterministic, but Nordhaus provides some uncertainty ranges for the most important variables. And what I've done is I've created 80% uncertainty ranges for each of the variables, and then I've looked at what would the impact be if we ran that uncertainty over its 80% range, and then I've ordered them here from biggest to smallest. Okay. What you find is that the top, and the middle there is 19.5. So this is optimal controls. The optimal controls I showed you, 19.5. And now what I'm doing is I'm saying, what if climate sensitivity was 1.5C instead? Okay, I'm not re-optimizing. Okay, so this is still under just the optimal control policy. Keep it simple. Well, damages would only be about 10 trillion. What if the climate sensitivity was really 5C? Well, then the damages are going to be 30 trillion. Okay? And that ends up being the top bar. And you go through the others there. I won't go into details, but one has to do with just how damaging is warming. What's the population going to be? At what rate does the atmosphere retain CO2? How quickly can we decarbonize, and cost of the backstop technology and so forth. Right, but what pops up at the top, at least an insight for me, is the biggest risk is the climate sensitivity here. And as far as I can tell, we're doing very little to address that risk. Right? We're working on things more towards the bottom of this tornado diagram than the things at the top. Okay? And so potentially SRM could play a role there in terms of addressing the climate sensitivity. Now, it doesn't directly change the climate sensitivity, but it would, for a given amount of CO2, if you offset the warming, it would have that effect. You can do the same thing on temperature. Okay, the 3.5C was the temperature change under optimal controls, and then I've looked at the sensitivities, and again, climate sensitivity is the biggest risk. Okay, let me hit two other things. So my takeaway from this is, hey, we should be focused on the top risk driver. At least we should be doing something here, right? Now the second thing is just how expensive I think emissions controls are really going to be if you're worried about the tails, okay? So what I have here is the probability of exceeding a particular temperature. This is an excess probability distribution. Probability of exceeding a particular temperature. Here's the temperature, and then the curves are the different policies. So the blue one is no controls, if we don't do anything. Okay, if we don't do anything, you can see there's about a 10% chance of exceeding 7.5C is the way you read this. 10% chance you'd go over about 7.5C, maybe 30% chance you'd go over about 6C. Okay, hopefully that makes sense. Well, you look at that and you go, even though the mean's 5, there's still this tail. Now, I look at that and I go, wow, I don't like that. I'd like to move that curve to the left. Right? I'd like to be as far to the left as I can be. Well, the way DICE does that is it imposes emissions controls. Okay, so if you spend 2.1 trillion and go to optimal controls, you're at the green line. Okay, and you might look at that and say, well, gosh, we still have, under optimal controls, the chance of going over 2C is still about 85%, right? And that's a threshold that scientists have said is dangerous. Right? Still a 10% chance of going over like 5C. Okay, I still don't like that. Let's move it further to the left. Again, if I'm just doing emissions controls, or if that's all I have, I spend 9.7 trillion more to get to the limit to 2C policy in DICE. Still, the tail is there. There's still a 10% chance of going over 3 and 40% chance of going over 2. And then you can see it gets increasingly more expensive to try to pull this whole distribution over and over to the left. And my argument would be that we may not want to do that. If we're worried about the tail and these large changes, we'd really like to have some kind of insurance that could cut off these tails. Instead of trying to pull the whole entire distribution to the left, well, we could focus on something that would cut off the chance of going over 4C, for example. And that would be something that potentially climate engineering could do. In fact, Linton and Vaughan, they conclude that it would appear that only rapid, repeated, large-scale deployment of potent shortwave geoengineering options like stratospheric aerosols could conceivably cool the climate to near its pre-industrial state on the 2050 timescale. And then other researchers have said that the cost to essentially reduce the risk of going over some of these potential thresholds is just politically infeasible. Okay. All right, 5 minutes. Okay, so I won't go into all the details here, but what I do is I build this decision model, and what I do is I say, let's assume we're following a policy of no controls or we're following a policy of optimal controls, okay? So I'm still allowing for emissions controls. And then let's suppose we're going to use climate engineering if we go over a threshold, or maybe we set some policy that we're going to do optimal controls, but if the temperature goes over 3C, we're going to deploy and hold it at 3C. That's the idea. And the question is, how valuable would that be? Now, could we even do that? Could you really manage the climate to that level of fidelity? Well, we need to do research to figure that out, I think. And I don't want to spend a lot of time on this, but what this is showing is just what is the value of climate engineering or solar radiation management as a function of where the tipping point is. So I'm assuming there's just one tipping point. If the tipping point is really far away, then it's not worth as much, right? And if the tipping point is close, then it's going to be worth a lot more. And it depends on your policy. If you say we're just going to wait until it gets really warm, or if we're going to deploy it at a lower temperature. But the axis is in trillions. Okay, so the technology, the ability to do this is essentially worth on the order of trillions, and that's not surprising because climate damages are in trillions. And the one thing about these technologies, it's currently believed that they're very cheap, on the order of billions to low billions to be able to do this. So we recommend an R&D program into this. Some people have worked up estimates on what the R&D program might look like and how much it would cost and so on. You can read about that in the paper. But I think this is an important chart, and what this is showing is how much solar radiation management are we using as a function of time under either no controls, which is the straight line, or optimal controls, which are the curved lines, and then if we're trying to hold to 2C, 3C, or 4C. Okay, so let's just say we're trying to hold to 2C, and this is under optimal controls. Currently, I showed you the IPCC estimates that aerosols are currently offsetting 1.2 watts per square meter. That's that little line across the top. Okay. So in these model runs, we wouldn't reach that level until about 2100. So the intervention would start out small and it would grow, and it wouldn't reach the level in terms of what we're already doing until about 2100. Now this might be in addition to that. There's different ideas for how to do this. If you want to hold the 3C, then it would be less, of course. And then on this axis, that is in terms of watts per square meter. This is in terms of how much matter you'd have to inject into the stratosphere in terms of teragrams of sulfur. The idea here is you'd inject sulfur into the stratosphere. And you get under 2C in the year 2100, we're at, easier for me to look here, at about 0.5 or so teragrams of sulfur per year. Okay, we currently inject 55 teragrams of sulfur per year into the into the atmosphere through our activities. So this would be 0.5 as compared to that. I'm not diminishing it at all. It's important to have these things in context, right? How big of an intervention are we talking about compared to what is currently happening and that the climate is experiencing? Okay, so the conclusion, direct benefits appear to be large. There's a lot of uncertainties left. Need to develop these technologies. This could have some impact on precipitation patterns, as might climate change itself, of course. I think it's important to bear in mind the choice is not a world without climate change or geoengineering, right? It's going to be geoengineering or what's going to happen if you don't do geoengineering. That's the choice you have to keep in mind. This could delay recovery of the ozone layer. Scientists are looking into this. And there, of course, there might be other unknown side effects. Another issue which I address in that climatic change article is when you stop doing it, then the effect would go away, right? So, the CO2 from coal plants stays in the atmosphere for a long time. The particulates, which are cooling, would come out very quickly in a matter of days. So, just like that, if you stop doing this, then the Earth would warm, and potentially more quickly, and you need to think through all of that. I talk about that in the paper. Okay, but this is only going to be resolved through research and development. Okay, so I think I'll stop there and then take questions. Yep. I'll let Eric handle the questions.
I'm curious, what's your political stump speech to get this to happen? If you have 5 minutes on a street corner, what do you say to the average Joe to get them to understand the long-term benefits of the research, where their tax money would go?
So I'm not a politician. I mean, the stump speech, I went through the 1 hour stump speech, but in my mind, I think the thing that kind of moves me the most is that the CO2 we've already put into the atmosphere, we may be committed to some large amount of warming, right, that we don't understand. The current things that we're talking about aren't going to address that, right? That's already happened. It's already in the atmosphere. So we should think about a backup plan in case the warming is higher than we think.
Hey, Dr. Bickel. Yeah, thanks again for coming and giving the presentation. So after taking one of your courses, actually, I'm extremely suspicious of pretty much everything I see regarding probability.
Especially me, yeah.
Yeah, because you like to trick us, so it makes it even worse. But in this case, when you see an output of $22 trillion of damage with a standard deviation of 3 trillion or whatever, are you pretty confident in those, or?
Highly, yeah.
You are? Okay.
No,
like you'd bet on that, or is it? No.
No. So, like in DICE is just a model, right? I think it's really useful in terms of understanding what are the big drivers, right? What kind of things should we be thinking about? Should we be worried about? What might the effect of the relative effect of different policies be? But it's a very simple model, right? And we're talking about a very complex system. So is the number really 19.5? I'd say absolutely not. But I have higher confidence when we put all these uncertainties together. I didn't do that here. We'd have the probability distribution that it's within that somewhere. But no, I wouldn't hang my hat on any one single number. So, the idea is to provide insight.
So the first thing I would suggest is never letting the coal industry see these data, because they might suggest that they just stop flue gas desulfurization, and there's the extra sulfur. But seriously, I guess I'm a little baffled by the climate risk information. And is my understanding correct that that is a a summation of possible synergistic effects that, say permafrost melting and the release of tremendous amounts of methane from that, and I mean,
So
how is that information quantified? I'm still.
So, sure, but quite have all of that. The dice model itself assumes that damages are relatively a smooth function of temperature change, that there isn't some discontinuity. Because that gets hard to optimize. It gets hard to figure out what is the optimal thing when you have these cliffs. Those damages in that model are tied to published, Nordhaus goes through published studies of climate change and what the effect might be, and they try to calibrate the model to that. I have another paper where I try to then put a cost on what the cost might be if we crossed one of these tipping points and you had a large methane release or something like that. The models aren't down to that level of detail. It doesn't have there's a methane release or something else happens over here. It's very aggregate and abstract, that if we crossed one of these thresholds, the damage might be 3% impact to gross world product permanently, something like that, but not down to the level of specificity you're talking about. That answer it?
Yeah, more or less. But I guess if your data concludes that is the highest or the best bang for the buck in terms of action, I'm concerned about the policy. How difficult it would be to get policy for something so unquantifiable.
Yeah. I mean, some of it's no more unquantifiable than climate change. And all these things you're bringing up would affect a model of valuing emissions reductions. Be the same thing. I had another thought I was going to mention, but I lost it. Sorry. So.
Well, thank you for the presentation.
Yeah.
Very nice. Just a few questions. Has there been a sanity check on the ability to generate that much sulfur without doing things like burning coal that would also generate CO2 while you're doing that? Where would you get it from in that quantity? Secondly, how do you get it, that mass quantity, up to the stratosphere? And third, are there any other perhaps problems with creating this massive acid rain cloud from putting sulfur up there? Just some basic from a non-chemist.
Yeah. So in the last one, there have been some studies in terms of what would there be an acid rain effect to this. I think most of the conclusion is not much. Okay, not much of an effect. This is it's in the stratosphere. It migrates to the poles and precipitates out at the poles. People have talked about just doing this in the Arctic, for example, not doing the whole Earth. But new studies might say no, there would be a big effect, so that needs to be looked at. In terms of the amount, it's 10% of what we're already doing. So it's not a massive amount. I mean, relative to what we're doing, it's a fraction of what we're doing. Ideas for working on this are to inject it. Marivold at Intellectual Ventures, I guess was it Microsoft? They have a design, and it's a single tether hose with a balloon of about 2 inches in diameter would provide what you need. So, yep.
Hi. My question is, I think the engineer side is important, but I guess there's another side maybe, which is people's willingness to pay, how much consumption they want to sacrifice to do this. I think combining these two together, you will have another optimization problem to solve. And also, have a second question is, what kind of impact for you to assume a log normal distribution, which has a kind of a fat tail instead of fitting like a gamma distribution?
Okay, so I remembered my one response. You made me think of one thing. When I showed the expert panel rankings, right, and they rank climate engineering first, that doesn't mean you're not doing anything else, right? This is not talking about just do this and you don't do anything else, right? They're recommending a portfolio of approaches, this being one, research into energy R&D being another, okay, just so. Now, in terms of people's willingness to pay, that is factored into this model in terms of how expensive emissions reductions would be, how expensive this climate engineering would be. These costs are, for solar radiation management, are almost zero in this model. I mean, they're 0.001 trillion, okay, compared to these costs for climate change are in the trillions. I mean, it's very, very inexpensive. That's one fear people have, is that any country could do this on their own. Any industrialized nation could afford to do this, where climate change requires everybody to work together. Emissions reductions require everybody to work together. This essentially would require acquiescence, I guess, of the great powers. If you're doing it, then nobody's stopping you. It's a much different dynamic, right? And then I didn't look at other distributions. There are some. I fit a log normal. I have that here. Go to point it out. I fit a log normal. There are other models. Keller has another model that's like an empirical distribution of what the climate sensitivity might be. It's very close. It's very close to this. For the types of results I'm generating, the uncertainty we're talking about, making changes to this, little changes to this isn't going to make any difference. I mean, what matters is that it goes from 1 to 7 or something. That's what matters. But slight little changes in that aren't going to have any real effect.
I'm just curious as to what the biggest pushback that you've seen when you make this argument for climate engineering. Is it related to the price tag or uncertainty with how it's going to affect the environment?
Yeah, the latter. It's not the former, because it's less than emissions reduction. So if you're willing to pay for those, then this is small. But people are worried that you're going to mess something up, right? That this is going to have a big effect. There's one Earth, and now you're experimenting on the planet. I would say there's some legitimate risk reasons. In my mind, a lot of people have an ethical reaction to it, that you just shouldn't intervene in the climate, even though we already are intervening in the climate. But for me, I don't see it that way. For me, it's a risk calculation, right? And this should be looked at. This should be an alternative. If it's a bad idea, then let's figure out it's a bad idea and get it off the table. But some people don't want it looked at because they think it will lower resolve for emissions reductions. And they've already decided that that's the optimal path.
I believe this is a second, possibly a third time I've seen you present on this material, and I must say it becomes slightly more palatable with repetition. That's a good thing on your part. Could you maybe give your quick summary of the top 3 aspects of the DICE model in terms of the negative economic impact of emissions control? Why is that such an overwhelming number in terms of negative economic impact? I've always been puzzled by that. And then just one upbeat message, I saw a little factoid that said in September, all of the generation capacity additions in the United States were from wind power and solar power, which is probably just an anomaly of plant timing. But we added a lot of solar power and wind power in September, and it was 100% of what we added.
So, how to answer that. The first thing that is not on this chart, but would be if you had any kind of range around it, is the discount rate. Okay, so DICE uses a market-based discount rate of about 4.5% real, I think. Okay, as you can appreciate, any positive discount rate means that benefits 200 years from now. It means that you would have to invest a small amount now to cover that cost in the future. So these results would be different if you had a different discount rate. If you said 0% discount rate, or something maybe like the Stern Review does, you might get a different answer here. Emissions reductions would be good, and we should go to 50% emissions reductions next year, right? In terms of the way DICE works, there's one is economic growth. It's a discounted utility of consumption model. So they basically, it's like a single person, and we're going to calculate the present value of their consumption over time. And so higher economic growth leads to more consumption, so that's better in the model. Emissions reductions in the model lower economic growth than you would add otherwise. And there's some abatement, there's some cost to implementing the emissions reductions. The exact numbers and functional relationship I don't have right here, but Nordhaus has several books. There's a very readable book called A Question of Balance, which is written for lay folks, and it goes through the model in an understandable way and talks about some of these issues. So I think, looking at that would be helpful. But the discount rate is, could completely change the results here.
Could you talk about ozone recovery?
So there were some early paper when this was first proposed, some papers around how it may create damage to the ozone layer to have the sulfates in the chemistry and have that in the stratosphere. There were some papers after that said it would delay the recovery that the ozone layer is currently undergoing, that it wouldn't make it larger, but it would delay how long it takes to be recovered. That's a couple, 2 or 3 years out of date. I'm not sure if there's been new studies on that. Part of the issue in arguing for research is there's just not a formal research program here. There's not a geoengineering directorate at NSF or anything like that. So a lot of this work, including what I've done, is just, it's mostly on the side, that you're doing when you have extra time, because you're interested in it. And a lot of some of this underlying scientific work has kind of been in that vein as well.
We are out of time. Let's
Okay.
thank our speakers.
All right. Thank you.